recording, so I'll start recording now. Okay, cool. Now we're recording. So that's why pressure is important. More people are joining. Okay, great. So what happens is when you open a can of Coke, is you notice it fizzes and it seems like the pressure is released, and that's exactly what happens. So when you open it, that's a bad picture, but there's the little thingy. Flip it, it's open. What happens is immediately the higher pressure from the headspace of the can equilibrates with the outside pressure. So this pressure is now decreased. And now the pressures are equal. I'll put P out equals P in. So if that's the case, that means there's going to be less force pushing on the headspace of the gas, of the liquid. And that means these gases can go out free. They go out more free. And that's why you get fizzing and carbonation once you open a can of Coke, or really a can of or a bottle of any carbonated thing, is you get fizzing. Because the CO2 molecules, and you really want to know the real reason, is because if you have an increased pressure in the headspace, it actually increases the solubility of the gases in the liquid. And then once you remove that force, you're kind of like physically pushing down on the carbon dioxide particles. But once you remove that force, the carbon dioxide solubility decreases, and that allows them to freely come out of the solution, out of the liquid solution, and go into the atmosphere and escape as CO2 gas molecules. So that's how can of Coke works. But we're going to be learning all the different gas theories and gas laws and everything. So there's this thing called the kinetic molecular theory of gases. And this is very easy. It sounds complicated, but it's very easy. And it basically says these four things. I think there's should be five, but I think, you know what's weird? They call it a kinetic molecular theory, but every textbook differs whether there's 4 or 5 of them. I don't understand that. It's supposed to be like a concrete thing. But anyway, basically it is a 4 or 5 definitions that kind of explain how gases behave. And it's pretty easy to, a lot of them are like, oh, no, duh. Like, it should make sense. So let's go over them. And the kind of questions I'll be asking on the exam with these is, I'll give you 5 choices. Which of the following is not true? Or which of the following is true? Stuff like that. I'm not going to have you memorize word for word the different postulates. So we don't need to do that. So here are they. Here they are in black. So the particles of gases are constantly moving. And along with that, I don't understand how to do this. So they're constantly moving, right? So, and they're moving in straight lines. And they're moving very fast. So the average, and here's how fast, the average kinetic energy of the particles is directly proportional to the Kelvin temperature. That's important. That's the most important thing. So what that means is, we obviously know they're moving, but how fast they're moving is strictly determined by their temperature. And the reason why is because gas molecules, and we're going to learn today, when we get to ideal gases, they're so small that their mass is almost negligible. They're, whether it's O2 or H2, O2 obviously weighs 32 grams per mole, where H2 weighs 2 grams per mole. There's a big difference there. But that difference is so negligible that their speed is virtually all determined by the temperature in Kelvin of their particles. Next, the attraction between particles is negligible. Particles exist no force on each other. So that's very important as well, because a lot of these we didn't learn it. We touched on polarity last class on Monday, but basically this means that all these gas molecules are going to be very nonpolar. So O2, once we learn about Lewis structure, this will make more sense, but O2 is oxygen double bonded to another oxygen, which is in our air. N2 is nitrogen triple bonded to another nitrogen. CO2 is carbon double bonded to 2 oxygens. Argon is just a noble gas, which is also in the environment. Hydrogen gas is also there in very trace amounts, but these are the main gases that constitute our air. And you notice about them is that I talked about polarity, how there's a difference in partial charge, there's a difference in the electrons in the covalent bond, kind of like a tug of war. The electrons will be pulled more towards one atom than the other. In this case, there is none of that. In these cases, for most gases, there is none of that, because You have 2 oxygens, 2 nitrogens, 2 hydrogens. Argon's a noble gas. It doesn't want to react with anything anyway. And then CO2, you can imagine there's an even pull this way and this way. But again, we'll learn more about that once we cover electronegativity, Lewis structure, and things like that. So if that really, the most important thing right now is that you know that the gases exist no forces on each other, and they don't really have much of an attraction to each other. So they're very inert. The word's inert, meaning they're not reactive. Inert. So that's important. Okay, so the next one kind of ties into that. When the moving gas particles hit another gas particle or the container, they do not stick, but they bounce off. In other words, the collision, that's a great line. The collisions are, oh my God, the collisions are elastic. So elastic collisions is very important. So those of you who took physics, that word should ring a bell. There's formulas and stuff, but basically what it means is they bounce off with equal and opposite force and conserve momentum. So that kind of ties into the second one where they're inert. Because if they weren't inert and they had some kind of attractive or repulsive force to one another, the molecular collisions wouldn't be elastic. They would be either partially elastic, inelastic, if they stuck together, or they would not be elastic. So, and this is very important because if you have gases, let's say this, if you had oxygen, right? Let's say oxygen reacted with other oxygen gas. If you had them in a container and there was a repulsive force or even an attractive force, let's say if there's a repulsive force. The repulsive force, once they come in close contact, would give them more kinetic energy when they disperse, when they leave the collision. If that's the case, eventually over time, pressure would build up so much that it would explode. That whatever container it was in would explode because the pressure would become so great because there was repulsive forces with gases. That would mean that you can't keep any gas in any container. That would kind of destroy the earth. That would ruin everything. You can't even, technically your room is a container. So it would you would die and suffocate and it would be terrible. Now, if the gases stuck together, that would be just as bad because they would stick together and they would react with each other and it would become so heavy that gravity would take it towards the floor. And the only way you can breathe would be if you're laying down on the floor, but then you'd still die anyway because all the gases would glob up together in one part of the room. So it would be a really shit show if these weren't true. Okay, so the fourth one is there's a lot of empty space between the gas particles compared to the size. So this is important too once we get into the ideal gas law and ideal gas behavior, because we're going to be making a lot of assumptions. We're going to be assuming that the gases are relatively the same size and they move at relatively the same speed, which is true when you're dealing with ideal gases and because their volumes are negligible. So here's an example. So O2, let's say O2 is this big, right? Let's say it's just that. H2 is probably around that big. So O2 is a lot bigger. So this is O2, this is H2. The distance between them is actually, I have this distance, but the distance between them is actually 10,000 times this. So if you have 10,000 times this, what's the difference between the sizes of these? It's not really that significant, maybe 0.00001%. So we can basically say the volumes of the particles themselves are negligible compared to the size of the container, but more importantly, the size between the molecules, the empty space between them. So that's how we can, that's why we can assume that. Okay, any questions so far? Either in the chat or verbally? No? Okay. And can you please mute your microphones if you have not? I hear some static from somebody else. Okay, thank you. Okay, so pressure. So pressure, I did say before, it is the force per unit area. So basically, there's different ways you can measure pressure, but And we're going to learn about the units of pressure in the next slide. But basically, yeah, so the way they quantify pressure in a lot of textbooks, and I like this definition, is that they say pressure is the force on the inside of the container, the force on the sides of the container. Because that makes sense. If they're moving faster, they have more of a force on the inside of the container, thus making a higher pressure. So that's a perfect example. So that's what pressure is. All right, this is an important slide. So from here on out, we're going to be learning a lot of gas laws. And it's important that we understand units. Now, these unit conversions for pressure will be given on the exam. The temperature one also with Kelvin, excuse me. But this is just to summarize all of the different units that we're going to be exposed to in Chapter 6 for all these different laws. And we're going to be comparing them and doing different equations with them. But pressure. So pressure, the main unit, the SI unit for pressure is what we call ATM, or atmosphere. So an atmosphere is based on the Earth's atmosphere. So that makes sense. Because we're an egocentric race, we think everything revolves around us, that we made our own unit around Earth. So the average pressure, the average air pressure on Earth is about 1 ATM, or 1 atmosphere. There are other units. So there's mmHg and torr. These are about the same. They're not exactly the same, but for our intensive purposes in Chem 1, they are the same. I think they're off by maybe a 0.01 something. And what this means, torr is just I don't really know where the word torr came from, but mmHg refers to a barometer. So a barometer measures pressure. And if you have mercury, just like a thermometer, if you have mercury, mercury expands and contracts not only based on temperature, but based on pressure, which is why it contracts actually. It's not because of temperature, it's because of pressure. So if you increase, yeah, it's actually a pretty cool thing. So thermometers, they don't change with respect to temperature. That's contrary to what people think. I'm gonna draw a thermometer. So I'll look at state 1 and state 2. So you have a thermometer, right? And it's up to a certain level of mercury. If you increase to a temperature equals, I don't know, 20. So if you increase the temperature to 100, this mercury has a happy pressure, right? Let's say this pressure is 1 ATM. Let's say it wants to stay the same as the atmospheric pressure. And what happens is it has an expansion level. So let's say that expansion level is 100 millimeters. If you have the same thermometer and you increase the temperature to 100, that mercury is the molecules are going to go faster. Even though it's liquid, just like gases, they're going to go faster. And the pressure in the headspace is going to be increased. So what's going to happen is the liquid is going to expand to try to relieve its own pressure. So the liquid will expand, and it'll expand to, let's say, 760 millimeters. So what this is saying, it's making equality. It's making an equality for a thermometer mercury expansion. So it's saying that, all right, at 1 ATM, at the normal Earth atmospheric pressure, mercury in a standard barometer or some kind of thermometer is 760 millimeters long. That's how much it expands. 760 millimeters in a standard barometer. So that's why this number 760, that's where it comes from mercury, from the expansion of mercury. The pressure associated with the expansion of mercury. So to be more specific. Okay, then you have torr, which is approximately the same thing. Then you have pascals. Pascals, we don't really use it too much in the formulas, but it does exist. And 1 ATM is 101,325 pascals. Okay, then is there any questions on those units, on pressure? Because these are new, we haven't dealt with them yet. I'm assuming most of you guys just woke up like I did, so maybe that's why you're quiet. So, okay. Hopefully I'm not boring you to death. But normally I make more jokes, but it's tough to do it on an online lecture. I wish we were in a classroom, but I don't want to commute. So I guess it's a give or take. Okay. So volume. We've seen volume before, and we're going to be measuring it milliliters and liters. For the ideal gas law, keep this in mind. For later on, we're going to cover the ideal gas law. There will be a specific unit. You have to use liters. You can't use milliliters because there's a constant involved, and it's a whole mess. We'll see that soon. Then you have amount. So amount is N, that's the variable, and it's the number of gas moles. Number of gas moles. Temperature, always Kelvin. Boom, we know what to do, right? We know always convert to Kelvin once we are given a Celsius temperature. Oh, I wrote the units down here. Wow, this is a really good slide I made. I'll pat myself on the back. Okay, then we're going to learn the first three. We're going to learn first four, actually. They're all very similar. Boyle's law, Charles's law, Avogadro's law, and the combined gas law. There's actually one more that we don't cover called Gay-Lussac's law. But anyway, for these laws, the volume unit doesn't matter as long as on the left side and the right side of the equation, they're the same. So we're going to be dealing with, so for Boyle's law, I'll give you the example. It's P1 V1 over equals P2 V2. The equations are going to be like this. They're going to be equating one case of pressure and volume, or two variables, from the first case and equating them to the second case based on a relationship, whether they're multiplied together or divided by each other. So this is the way the laws are going to look like. So what I mean by volume doesn't matter, that refers to V1 and V2. It doesn't matter if they're if they're liters or milliliters, as long as V1 is equal to V2 in the same units. As long as if V1 is milliliters, V2 has to be milliliters. If V1 is liters, V2 has to be liters. That's important. Same goes with pressure. Same goes with mole, or no, N is always moles. There's nothing else you could make it. Volume, pressure, temperature. Temperature is always Kelvin. So yeah, really pressure and volume are the only ones that it doesn't matter for these laws, as long as it's the same on the left and the right side of the equation. For ideal gas law, it does matter, but we'll get to there in a second. So temperature is always Kelvin. Regardless what law you use, temperature is always Kelvin. So now to wake you guys up, I have a question. Someone can answer it. Why is temperature always, let's say, why is temperature always Kelvin? But let's look at a case. Charles's law, P1 equals, P1 over T1 equals P2 over T2. So why, in this equation, why can't we have it just like pressure, where the left side and the right side are the same? Why in temperature we have to make both of them Kelvin? So can anybody answer that? There's a chat. So that T can't be negative. That's true, but pressure pressure and volume can't be negative, but that's not the reason. It's a good point, but that's not the exact reason I'm looking for. So why can't pressure, or why can't temperature be, why can't it just be Celsius, Celsius? Tyler, good answer. Good answer. That's closer, but not really on the ball, not really on the point yet. So pressure, we can have this 1 and 1, or like for ATM, we can have it 1 ATM, 2 ATM, or we can have it 760 mmHg, 1,520 mmHg, and it wouldn't matter. We get the same answer. But for temperature, we can't have Celsius, Celsius. And it doesn't have to do with them being negative or 0. So think about the definitions of the units. Pressure, to get from one unit to the other, or really any other unit except for temperature, what do you have to do? You either multiply or divide, right? So that's a hint I'll give you. For pressure, let's say we want to convert from ATM to mmHg, we're multiplying by 760. For volume, milliliters, and liters, we're multiplying by 1,000. Temperature, we're not multiplying, we're doing other things to it. So, can someone answer? Yes.
So my first thought was that like 'cause Celsius is a temperature regarding like the boiling point and freezing point of water, and then Kelvin's more of like a universal temperature. That's just why, because whenever you do a temperature calculation in other things, you usually use Kelvin too. So that's why I thought that.
Okay, so yeah, that's closer that's closer. So it has to do with the absolute unit, right? So I guess I'll give you guys the answer. I'll stop torturing you, unless anyone else has another thought. Okay, I guess I'll stop torturing you. So it has to do with the multiplicity. So here's what I mean by multiplicity. If you have Celsius, even though Celsius and Kelvin are based on the same unit, they're just different, just moved over. If you have 1 Celsius, and I want to double that, what is it? 2 Celsius. If I have 1 Celsius in Kelvin, that's 274 Kelvin. What's 2 Celsius in Kelvin? 275. You can see how, if I put Celsius into an equation, this would be double this. This is times 2. This is not times 2. Meaning, if you're dealing with equations that have multiplication, division, whatever, on the left and right side of the equation, the multiplicity of Kelvin and Celsius and even Fahrenheit, they're all different. So that is something that's unique for temperature. It's not really encountered with any of the units we deal with in this class, except for temperature, that the multiplicity is different. So that's why you always need to have Kelvin. And you kind of saw this on, I think it was your first homework assignment, where you had to determine Celsius per second or something. You need to determine a rate. You need to convert Fahrenheit per minute to Celsius per second or something like that. I think you remember that. Some of you do. And some of you, what you were doing is you were just finding the difference in temperatures in Fahrenheit before you convert it to Celsius. And you'd see you'd get the answer wrong. And this is the reason why. Because the multiplicity, the relationship between one temperature and another in Fahrenheit is different in Celsius and is different in Kelvin. So that's the reason. So that's cool. Okay, so now let's get into the gas laws if there aren't any other questions. So basically, here are the gas laws. Here's all of them. And we're only going to be, really, it doesn't matter. I don't think the textbook covers Gay-Lussac's law. Some textbooks do. I cover it because it's comprehensive. That you have all of them. So here's all of the simple gas laws. Here's ideal gas laws here. Here's all of them. Here's every law. All right, we're done. No, I'm kidding. But here's the laws. Boyle's law is P1V1 equals P2V2. This is a really good slide. It just covers everything. I will be giving you these laws on the exam. So you don't need to memorize the equations. Just understand how to use them. So you see how Boyle's law references pressure and volume, and it relates to two. They have an inverse relationship with each other. What that means is at a constant temperature, because temperature is not in here, it's constant, the pressure increases, the volume has to decrease. And we'll do examples of all those. I'll go through like the theory of each one, going through cases of where that makes sense. Mathematically speaking, if you have two things multiplied together in one side of the equation, that means they're inversely proportional. So what that means is, why that is, if I increase pressure, let's say we have P1 and V1. So let's say P1 equals 2, V1 equals 2. And let's say P2 equals 4. So in the equation, you'd have 2 times 2 equals 4 times V2. The only way to make this equal is if the volume goes down. The volume will go down from 2 to 1. So V2 would have to equal 1. So That's why it's inverse. That's how it's an inverse relationship. So one goes up, one goes down. Charles's law talks about a directly proportional relationship between volume and temperature. And this makes sense. If you think about a gas at a certain temperature, if you increase the temperature, what's going to happen to the gas? Oh, it's going to expand if the pressure is held constant. It's going to expand. So if it expands, the volume increases. That makes sense. Then with pressure, let's say the volume is kept constant. So it means it's in a container, it can't leave. Let's say you take a bottle of water or a bottle of anything and you leave it outside and temperature increases, right? Leave it on the blacktop. Temperature increases. The pressure of it will increase also until it explodes. So the pressure could be released. So that's a direct proportionality. Then you have the combined gas law, which is, if you look at the first three, it's literally combined. That's why they call it that. It's combining the first three laws into one simple law. That if you know how to use the combined gas law, you're good with all of these. But the thing you have to keep in mind is whatever question you're dealing with might have a constant volume, constant pressure, or a constant temperature. If that's the case, that means if, let's say it's constant volume, you cross out volume. If it's constant pressure, you cross out pressure. And then you are remaining with one of these laws. So it's, once we do practice examples, it'll make more sense. But what I'm trying to get across is that they are all related to each other, and they could all be explained by is that a bug on my neck? What the all right, sorry. I was like, I hate spiders, so I'm like, I always have this fear that a spider is gonna like come down. Not always have the fear. It's kind of, it's not full-fledged arachnophobia, but I just really don't like spiders. Every other bug I'm good with, but not spiders. That's why I have a cat. She can eat them, but that's not why I have a cat. But anyway, she has eaten a spider before. She's eaten a centipede before also. She saved my life. Okay, so the point is I'm trying to get across with the combined gas law is that it's a combination of the other three. And if you know how to use it with knowing what's constant, you can solve any question with it. Then you have the ideal gas law, which is separate. So if you're looking at all the laws, you see P, you see V, you see P, but you know what N is. But now you have this thing R. And we're going to cover R. So R is the ideal gas constant. So R is the ideal gas constant. So that constant, there's several definitions of it. We are going to focus on just one of them, and that will help us understand why we need to use the units for pressure, the separate units, the distinct units for pressure, volume, N for moles, and P for temperature. Okay, any questions on that? I know I kind of ranted about them, but now we're going to go in depth about each law, and it'll be faster because you've already seen the equation before. We'll go over why it's like the theory behind it, and then we'll do an example. So that's what we're going to be doing. Okay, so first one, Boyle's law. So Boyle's law, inverse proportionality between pressure and volume. And the equation, P1V1 equals P2V2. So I said that again, I said that already, but here is the example. So let's say you have a certain pressure of 1 atm on a certain volume of gases. And this is a piston, by the way. So this cylinder, this really thin cylinder, could freely float up and down. And it can kind of release the pressure, make more pressure by pushing down on it. So let's say you have pressure at 1 atm and the volume is at 1 liter. If you increase the pressure at the same exact time, what you're doing is you're decreasing the volume. So if you're increasing the force you're putting on in this unit area, force per unit area pressure, increasing the pressure, that decreases the volume. That makes these molecules move faster because now they have less places to move and they hit the container more. So it creates more of a force on the inside of the container, making more pressure. And if you do this in the equation, as it's written here, you have, so P1 is 1, V1 is 1 equals P2, which is 2, times V2, which is 0.5, and that works. And you see how the volume will go down as the pressure goes up. And if you go vice versa, the opposite will happen, where the pressure decreases on the left side here, and then the volume increases as a result of that. Okay, so now example from the homework. So just pay attention. All right, so you have a 50-liter cylinder containing helium gas at a pressure of 15. Now, these gas questions are going to all sound the same. They're going to give you a bunch of information, and it's going to ask you a question. So what you can do is first write down everything you're given and read it slowly. So a 50-liter cylinder, all right? V1 is, I'm going to make it 50. Helium gas at a pressure of 15.3 atm, all right? P1, 15.3 atm. Is used to fill a weather balloon in order to lift equipment into the stratosphere. To what maximum pressure in atm could a 285-liter balloon be filled? Okay. So this is saying this question is actually more complicated than this. But okay, I think this is meant to be simple. I can explain difficult gas problems in a bit, but so using Boyle's law, we have the volume 2, V2, is equal to 285 liter, or not 2, okay, undo, 285 liters. Get the pen back. 285 liters. Now we're looking for our pressure. So what is our P2? So V1, P1, V1, 15.3 times 50 equals P2 times 285 liters. Now we divide by 285 and we get P2. Whatever that is. So I turn my phone off, but I'll do it in my computer. So 50 times 15.3 divided by 285, 2.68. So 2.68. And I think your numbers are going to be different. 2.68 ATM. Okay, cool. Any questions on that? And technically, all right, you want to know technically? Technically, this answer is wrong. But I think Moodle gives you right because this is like a simple Boyle's law equation. But I'll tell you why. And this is important, so I do suggest to listen for understanding. And I think the test might have some like one crazy problem with this concept. So whenever you're dealing with a cylinder, right? A gas cylinder, like, you know, like a tank, propane tank, butane, whatever, like this gas tanks, helium in this case. Think about how it works, and I'll tell you how it works. You release the pressure, right? It comes out. You hear tss, and it comes out until a certain point. That point isn't when all the gas is released. That point is when the pressure from the inside of the container is equal to the outside pressure. Basically, if you're just in an atmosphere, in outside, you release a tank, it will fizz out, all the gas will fizz out until the inside of the container is 1 atm, and it's the same as the outside world. The reason why it does that is because that everything, really everything in the universe works in a gradient. That's how things happen, by gradients. In this case, a pressure gradient, otherwise known as a pressure differential. So if you have higher pressure, which is, you can see in this container, 50 liters of 15.3 atm. That's a lot of pressure. if you have a higher pressure on the inside of the container and a lower pressure on the outside of the container, 1, the 15.3 is going to leak from high to low. Always, the gradients are always from high to low, naturally. So the high pressure will go to low pressure. Just like that's how weather works. That high pressure goes to high goes to low in order to make an equilibrium. So does that make sense? That it will release, the gas will release from high pressure to low pressure until the pressures are equal. If they're equal, or when they're equal, no more gas will be released from the cylinder, from the tank. That's important to know. That means all the gas isn't going to be used. So technically, this answer is not right. So I'm gonna show you how to figure out the right answer. But before I do that, is there any questions on what I just said? Because it might be a complicated concept. And I'm definitely gonna have a crashchem.com video on this because nobody really talks about that. And I don't even think it's in the textbook. Is there any questions on that? No? Okay. All right. So here's how to actually solve this problem. So, where's my pointer? There it is. I'll do it over here. Now, you can say the amount of gas, let's say quote unquote amount, refers to the P1V1. So let's just say P1V1 equals amount. So whatever pressure times volume amount you have. So the pressure times volume amount we have in the cylinder is 50 times 15.3 ATM, which I just calculated before. Let's see, 15.3 is 765. 765. I'll just put, that's the amount. 755. 765. Okay. So what we're trying to do is we're trying to see how much gas we have until, oh, I mixed these. This was P1, V1. Yeah. Okay. So what we're trying to do is figure out how much usable amount we have. Sorry, I just said that at a louder volume, but it's important to know usable volume. We can't use all of it, or usable amount. We can only use the amount that gets us from 15.3 to 1. So we can solve it again. We can do how much can we actually get? So if we have case 1, which is 765 equals, there's different ways to solve this. You could do technically the usable amount is, well, actually the easiest way to do it. There's different ways. The easiest way to do it is do 15.3 minus x equals 1. So that's going to be 14.3. So the usable amount is actually 14.3 because that one ATM of pressure in that 50 milliliter, that 50 liters is going to be there, is going to always be there. So if you have, well, actually technically, wait. Yeah, you get the same answer. Does that make sense? If that makes sense, here's another way you can do it. The non-usable amount, the amount that will stay in the container, will be 50 liters times 1 ATM equals 50. That's the amount, 50. Because if you have a container of 1 ATM, it doesn't matter what the pressure is. If it could be 15 or it could be 1. If it's a container with gas in it, the volume will take up the volume of the container. So it doesn't matter if it's 1 liter or 50, or sorry, it doesn't matter if it's 1 ATM or 50 ATM. The volume of it will still be the same. So 50 amount is the amount of gas, okay, particles. The 50 particles is the amount that we cannot use. So the usable gas is our total, 765, minus our non-usable. So that's going to be 715. So 715 is our P1V1 of usable gas. Usable. So that's how you, so basically the answer using that 715 would be 715 equals 285, which is V2 times P2. And then you would divide that and you would get 715 divided by 285, and you get 2.51. So it's close, but not exactly. 2.5, there it is. So P2 equals 2.51. Okay, I know that was a lot, but is there any questions? And there should be questions, unless you're not listening, but that's an important concept, that containers and cylinders that are pressurized, they don't use all of their gas. They only use the amount of gas that it takes to equilibrate with the environmental pressure. Does that make sense? Oh, there's a chat. Let me see. Can you go over how you got the 50 again? Okay, so Sarah has a question, then I'll answer your question. So this 50. So if we say that P1V1 is the amount of gas, right? Let's say 765 is the total amount that we have in the cylinder. The amount that is usable, the amount that we can use, is when 50 liters of 15.3, it fizzes out until the pressure is 1 atm. So when the pressure is 1 atm, how much gas do we have? All right, 1 times 50, because the volume is always going to be the same, 50. So 1 times 50 is how much we have after equilibrium is achieved. So if that's the case, then 765 minus 50, which will be our usable amount of gas. And that will be our P1V1 usable. So that's how I got the 50. It's the non-usable. Because we can only go until we get 1 atm. We can only release pressure until we go to 1 atm. Oh, the 14, oh, okay, so Nick, the 14.3, it wasn't used, but you could also use that. So let's say if I did use that. So if 15.3 could be our adjusted usable ATM. So like I said before, there are two ways of solving this. So let's use the 15.3. Our usable will be 50 times 14.3, and you can solve that and you'll get 715. So that's an easy way to get our usable again, instead of doing the subtraction. But I want to do the subtraction just so you can see where I'm getting that from, instead of just going in one step. Okay, cool. All right, I know that was complicated, but it's not going to, so gas law problems are tough. And when I was first teaching this class, I didn't make the tests or anything. I still don't make the tests during the regular semesters, but for the summer I do. I got thrown off a bit because I didn't expect them to give these kind of really complicated problems where, oh, you have to assume a cylinder, like, oh, don't you know what a cylinder does? Like stuff like that. So I needed to like adjust my teaching to that because I've never seen that. So Venk, that's what I was going to get to. It's a really good question. So on a test, we use method 2. Now, on a test, I'm not going to ask cylinder questions. Well, actually, technically, okay, for a cylinder, always use the second method. That is the correct answer. That is the correct answer. The first answer is wrong if you're dealing with a cylinder. But I think Moodle doesn't really care about that right now. But the other questions, it's not going to be really a cylinder. It's going to be, let's say you have one container into another container. So whatever. It's going to be some kind of problem that's not dealing with cylinders. But once you're dealing with pressurized gas cylinders, you have to do the second method, which there's a usable volume, a usable amount, and a non-usable amount in that entire cylinder to make it equilibrate with the atmospheric pressure. So we'll do more examples now with other laws. Don't freak out. Don't think, oh my God, they're all this difficult. No, they're not. So the other ones are easier because we're not really dealing with temperature and stuff. But for the 1 ATM, you're assuming it's on Earth. Yes, you are. You totally are. That's probably why Moodle doesn't do that. It just has a simple, it does a simple approach, the method 1. Because they didn't write, oh, assume you're on Earth and assume the atmospheric pressure is 1 ATM. They didn't write that. But I just wanted to show you that in like a real tricky gas problem, if you have a cylinder, that's the method you want to use. And I didn't learn that in undergrad either, so I'm glad you're learning it now. Okay, so let's move on to the next law. You'll see it'll get a little bit easier. So Charles's law. Charles's law involves volume and temperature. So it's a direct proportionality. As the volume increases, the temperature has to increase as well. Or as the temperature increases, it causes an increase in volume. And here's an example of that. So let's say you have ice water and you have a balloon. So what's going to happen is, or this works with tires also. So let's use this example, then we'll talk about tires. So ice water, it will actually compress the gas because it's colder. The molecules are moving at a lower kinetic energy. The gas will compress. There will be a low kinetic energy, and then therefore the volume will decrease. Boiling water or hot water, warmer than ice water, the kinetic energy will be fast. The molecules will want to move faster because the temperature is higher. What that will do is it'll create more force and it'll expand the container. And you notice how pressure is held constant here because the container has the ability to freely expand and contract, meaning the container, the balloon, has the ability to do that. So the volume will increase because the gas molecules are putting more pressure on the inside of the container. In order to relieve that pressure, to keep it at a constant pressure, the balloon will have to expand. So that's how Charles's law works in a molecular view. So here's a definite explanation of what I just said, and we'll do an example. We'll hide the answer. We'll do that. Okay, so here's what I mean that they're not going to be as crazy complicated. All right, so a container, doesn't say a cylinder, or a pressurized whatever. A container holds 50 milliliters, all right, so V1 equals 50, of nitrogen at 25 Celsius. So T1 equals 25 plus 273 equals 298 Kelvin. And you notice that immediately with a Celsius temperature, I converted it to Kelvin. Always do that because like we mentioned before, but if you're on exam and you're freaking out or whatever, you're just gonna randomly write down things if you have test anxiety, like I do. But if you write down every time you see Celsius or if you ever see Fahrenheit, always convert it to Kelvin immediately. You can use that number once it comes time to calculate. All right, next is blah, 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 and a pressure of, and a pressure of 736 mmHg. What will be the volume if the temperature increases by 35 Celsius? Okay. So what will be the volume? We don't know. So V2 is unknown. The temperature 2 is going to be increasing by 35 Celsius. So 25 plus 35 is 60. So it'll be 60 degrees Celsius plus 273 equals what? Nice. Equals 333. And yeah, I could have done that in my head, but I didn't feel like it. Equals 333 Kelvin. Okay. So keep in mind here, this is a Charles law practice problem. That means we have V1 over T1. Nope, V1 over T1 equals V2 over T2. T1 equals V2 over T2. But the question is giving us pressure. Pressure. What the hell do we do with it? It doesn't talk about pressure and the rest of the problem. It just says it once. So you assume it's constant. Sometimes you may be given unnecessary information. So just like the work state, the pressure in state 1, hold on, someone's joining. The pressure in state 1 is 736. The pressure in state 2 is 736, meaning the pressure is unchanged. So we can ignore pressure here. It's held constant. So we can just use Charles's law. Sometimes the questions might say, assume the pressure and moles are held constant. But in this case, it's telling you that in a more tricky way by saying the pressure is 736, but nothing happens to it. So we can solve, and we could do 50 milliliters over T1, which is 298, equals V2, which is unknown, over T2, which is 333. So we can multiply both sides by 333.
Question?
Yes.
We need to use Kelvin if we want to use any of these pressure laws.
Every single one of these laws, Kelvin is your go-to. You have to use it for temperature.
Okay.
Okay.
That's part of the.
Yep. What was that? Sorry.
That's part of the general rule set or something like the. Because are there specific values you need to use for these type of questions?
So for temperature, for every law, temperature is always Kelvin. For these laws we're learning about now, Boyle's law, Charles's law, Gay-Lussac's law, Avogadro's law, combined gas law, for volume and temperature, right, for volume and pressure, it doesn't matter as long as they're the same on the left and the right side.
Okay.
So in this example, we're using milliliters on both sides.
Uh-huh.
But for ideal gas law, that's the last one we're going to learn, it does matter. That's the one with the constant.
Oh, okay, ideal gas law. I'm getting ahead of myself.
Yeah. So, you took the class before, so like.
Failed the class before.
Well, you took it, so you have exposure to this, which is
yeah.
So yeah, we'll get to ideal gas law in a second.
All right.
All right. Cool. Good question. All right. So we do the math, we do the stuff, and we get V2. V2 is 333 divided by 298 times 50. We get 55.9 milliliters of nitrogen. So that's important. All right. Cool. So we got the answer for that. Any questions on that one? That's a pretty simple Charles's law example problem where we just plug and chug. Or we have 3 of the variables, we have 1 missing, which is V2, and we solve for it. Okay, moving on. Avogadro's law. Same concept as Charles's law, but we are making an assumption, not assumption, we're making a comparison between volume and amount in moles. So the equation, which I'll write down, the equation is V1 over N1, which is the amount in 1, equals V2 N2. And this makes sense because if you have a container, or if you have a balloon, let's say you have a balloon, or if we have to talk about tires. I'll talk about tires in a minute. But if you have a balloon and it has a certain volume and a certain number of moles, if you inflate the balloon, what are you doing when you're inflating the balloon? You're pumping more gas into it. You are increasing the amount of moles. If you increase the amount of moles and the pressure and the temperature are held constant, like written over here, what's going to happen is the volume will increase and the balloon will become more inflated. And then that's how Avogadro's law works. You're increasing the amount of moles, that increases the space they take up if the pressure and temperature are held constant. So let's get back to Charles's law real quick for tires. So some of you, probably most of you drive, and if you do, you know that, let's say it is the winter, your tire pressure will be a little bit less. than the summer. The reason why is because of Charles's law. The cold temperature around the tire will actually compress the gas. It'll make the gas inside your tire move more slow, and it'll decrease the pressure, decrease the tire pressure. But in the summer, or even in the winter when you drive, so let's say, so here's a good experiment you can do. If you have a tire pressure sensor in your car, or even the newer cars have that, but older cars, you can just take the cap off and you have a meter, and you stick the meter in for a second and it gives you a pressure. Here's an experiment you can do. Now it wouldn't really work in the summer because everything's hot all the time, but in the winter, if you ever remember this, you can take the tire pressure before you drive. Let's say you leave the car overnight and leave it outside. Take the tire pressure on a really cold day before you drive. Let's say it's 25 pounds per square inch. Then drive for 30 minutes, 40 minutes, or whatever. Drive for wherever you have to go. Drive for like 40 minutes. Take the tire pressure again. It'll be higher. And the reason why is because the tire is rubber and it makes friction with the road. That friction with the road at very high RPMs of tire rotation actually increases the temperature of the tire, thus increasing the temperature of the gas inside of it, making them move faster. So you can actually see Charles's law in action, and you can actually calculate. You can actually calculate it. If you have the temperature before and after, which I don't think it's pretty difficult to get the temperature after, but if you have the temperature before and after, you can calculate the pressure increase. Or you can calculate based on the pressure, you'll have the pressure increase. You can calculate based on the pressure increase and the outside temperature before, what is the new temperature in the tire using those numbers. So that's a little cool experiment you can do. So yeah, email me if you do that. I'll be pretty, because I don't think I've had students do that yet. Okay. Avogadro's law, we know this. As gas increases, volume increases. Yeah, it makes sense. All right. Okay. So I don't think I have an example for that one, but it's pretty easy. Next, the combined gas law. The combined gas law involves Boyle's law, Charles's law, and Gay-Lussac's law, which we did not cover. Avogadro's law, it doesn't really cover, but basically, here's the ideal gas law. P1V1 over T1 equals P2V2 over T2. There's nothing really else to it. I kind of explained the hell out of it already. Are there examples? Yes, there are examples. Okay, so hold on. Okay, so we have that law. After I explain the ideal gas law, I'm going to give you a 5-minute break it's going to be a break for me, not a break for you. It's going to be a 5-minute answer these 3 questions kind of break. Okay, but before that, PV equals nRT. So the ideal gas law, units matter. For this one, the units matter. So PivNert, that's otherwise known as PivNert, if you've ever heard that before. PV equals nRT. So basically, this is saying that we can assume that these gases take an ideal behavior. And I'll explain what ideal means in the later slides. It has to do with the size doesn't matter, kind of like the kinetic molecular theory of gases that I explained before. It's kind of like that. But basically, you have something different here. We know what P is. We know what V is. N is the number of moles. R is nu. P we know is temperature Kelvin. R is called the ideal gas constant, or the gas constant. And it depends on the units of P and V. Also T and N. I don't know why it just says P and V. It depends on the units of everything else. So these other gas, the ideal gas variables have to be a specific value to use a specific R. There are different R values. So if you read the textbook, it will confuse you. It will give you a table of R values. There's like 10 of them. And it'll give you different units that they're associated with. And here's 2 of them right on the bottom here. The one we're going to use, and the most common one for chemistry, if we end up taking thermodynamics, you're going to use the top one, because you're dealing with energy. But for chemistry, we use the bottom one, 0.08205, or I say 0. Here's the way I write it on the exams, 0.08206. And the unit is liter ATM divided by Kelvin mole. That's the unit, the big unit. And I'll explain to you, or I'll show you how this works and why. I'll show you why all the units need to be their specific values. Different color. Okay, so all right, go over here. Why is the thickness of, there we go, right, better. Okay, so I'm going to write the ideal gas law. I will write it in just the units. I won't even write numbers or variables, just units. So ATM is pressure, volume is liter, ATM liter equals N, which is moles, times R. Now the units for R, like we just said, is liter times ATM divided by Kelvin mole. And this is going to be times temperature, which is Kelvin. All right, so all of that is the ideal gas law written out in units. Now, in order to check it works, we can do this. Mole cancels out with mole. Kelvin cancels out with Kelvin. Liter cancels out with liter. ATM cancels with ATM. And that means the equation's valid. That means the equation works. So that is exactly why we cannot use milliliters or mmHg or any other unit besides these specific units, liter, ATM, Kelvin, and mole, for the ideal gas law. The other ones you can. I mean, always Kelvin for temperature, but the other ones you can. You could use milliliters, you can use mmHg. I think that's it. But you can use other units, is what I'm trying to say. But for ideal gas law, it all depends on what constant you're using. All depends on what constant. So does that make sense? And there's one more thing before we go into these practice examples, is that I'll give you a hint. Moles, right? Moles is moles. That's the hint. No, but let's look at the problems. Now, going through this, you see in number 2 and number 3, I don't give you moles. I give you grams. But now that we're experienced chemists and knowing chapters 1 through 6 or 1 through 5, you should be able to get moles from the grams if you know what it is. So in some cases you don't know what it is, but you can figure it out, like number 2. So try these on your own. Number 2 might be a little complicated, but try these on your own. And I think these are all ideal gas law. Yeah, these are all ideal gas law. So try these on your own. I will give you, it's 10:09. I'll give you till 10:18, 19. I'll give you 10 minutes. I'll give you till 10:19. And then I'm gonna get theoreal. And then I'll be right here though, so you can ask me questions in the meantime. All right, go. And I'll ask you guys to answer them for me, to give me the answers. So just the number answers, then we're gonna go over it and see if your answer is right. But I would need the number answers from at least one of you. So don't just not do it. And don't think, oh, someone else will probably, one of the studious kids will probably do it. But if everyone thinks like that, nobody will do it. So at least give it a try. Okay, Nicole, I see your answer. I didn't get that. Did everybody else get that? Maybe I'm wrong. I did it too fast, maybe. And Olivia, yes, I got 53 as well. Let me get a PR table. Oh, okay. Yeah, maybe 182 is the first one. All right, well, I'm an idiot then. We'll do it together. 53 though. So with atomic, 53, or I got 52.2 to be exact. 52.2 divided by 2 is 26. That doesn't seem to be one of our diatomics. All right, maybe it's a really bad question. All right, whatever. Yeah, I mean, technically, chromium does have 52, but it's not a gas. It would never be a gas. It's a metal. So, I mean, it could be. If you make it a metal. All right, good job, Tyler. I think you got that right. I didn't do it yet, but we'll do it together. All right, let's do them together. Okay, so let's do these three together. I'm gonna need your help. Oh my God, stop. I'm sorry. She's like jumping at everything. Last thing I need right now. All right, so here's what we're gonna do. We made 3 separate slides. Oh my God. She sees shadows on the wall and she goes crazy. All right, so let's do this. Okay, the first one, we have all right, so we have 60 liters. So our volume equals 60. Chlorine gas at 27 Celsius. So T equals 27 plus 273. That's an equal 300. Is that right? Yeah. Okay. Then our pressure is 125 atm. So pretty big pressure. When the leak was discovered, the pressure was reduced to 50. Oh, I'm an idiot. Oh, that's why. It was reduced to 50. I didn't even see that 50 part. How many moles of chlorine gas escaped? Okay. So here's what we can do. So we can do the PV equals the PIV inert. My thought is the PIV inert before, and then compare it to PIV inert after. That's one way to do it. So a thing is, for these gas laws, if you think of a more intuitive way to solve it, go for it. And then there are different ways to solve it. You can use the ideal gas law for problems that involve the combined gas law or Boyle's law. You can do that, but it may require maybe one or more steps. But either way, you can get to the answer in multiple ways. So if you don't agree with this way, this is just I'm very simple, so I have to try to think of the most simple way to do it. So I'm like, all right, we have a PV and a T before, and we're dealing with moles here. That's the key thing. That's why I'm using PIV inert, because it's asking for moles. So we can figure out, all right, moles before, moles after, subtract the 2, and you get the answer. So P1 for the first before, so I'll write before, it's going to be 125 times 60 equals N, which is unknown. Our ideal gas constant is 0.08206. And our temperature is 300. So can someone tell me what they got for N here? This is where I'm going to need your help for these things. Anybody? 301. Good. Wait, I got 30. I did this part. I got 304. Whatever. It might be a rounding thing. Yeah, Tyler, I got 304.7. Whatever. Close enough. So, I got 304. Venk, maybe you're rounded wrong or something, but not wrong, but just a little bit different. Yeah, 304. Okay, so 304. So this is our moles before 304. Now after, same thing. So the volume doesn't change because it's a leak in the same container. In this case, a spring. What happens? A tank. It's a tank. So we have the same container. So our volume's the same. Our pressure was reduced to 50. So 50 times 60 equals our new N, and after 0.08206, and the temperature remains constant as well. And then we solve for our new N, and what do we get for that? Oh, my bad. Excuse me. So what do you get for the new N? 121.86. All right, so we'll round that to 122. 122, and then you subtract both of them, the before moles minus the after moles, to see how many were released. And what was that, 182 or something? 186? Someone tell me. I'll look up in the chat. 182.9. Thank you. Okay, cool. All right, so 182. All right, awesome. So that's how you get that. Any questions on this problem? We are gonna have to go a little bit faster for time's sake, but we should be good. The rest of it is just like either examples or definitions. Yeah, we'll be fine. Okay, so the next one . The next one is we have a certain mass. So we have 96 grams of a gas occupies 48 liters. We know V is 48. The pressure is 700 mmHg. Automatically, so I'm going to convert this to ATM because I know when I see grams, when I see molecular weight, stuff like that, I know that I'm going to be using the ideal gas law. And if that's the case, then I need to be in ATMs. So this is around 0.8 or something. 700 divided by 760, 92. So 92 ATM. Okay. Then our temperature, same thing, not FT. Our temperature is going to equal 20 plus 273 equals 293. What is the molecular weight? Whatever. So let's do PV equals nRT. So P 0.92 times V is 48 equals N, which is unknown, R, which is 0.08206, and P, which is 293. Now for time's sake, I'll just cut to the chase. N is 1.839 moles. And if that's the case, what are we being given? We're being given a sample. Where am I at? So a sample of 96 grams of a gas. So we know that 96, stupid thickness, that 96 grams, or of any sample, let's just go generally. So grams equals the amount of moles we have times the molar mass. That's the definition we learned a few chapters ago. So we have 96 grams of a sample, and we have 1.839 moles. What is the molar mass? And if you calculate that, the molar mass is 52.2 grams per mole. And normally the question would be, what is this gas most likely to be? Unfortunately, 52 doesn't really fall into a category of being any gases. I don't know where I got this problem from, but maybe I made it. Maybe I was just dumb. But it's about the molar mass of chromium, but chromium is not really a gas. But normally in this kind of question, I think there's probably one like this in the homework. You'll get round numbers, like you get 28, which in that case it would be N2. You'll get 32, which would be O2, stuff like that. Or you might get a noble gas. The question?
Yeah.
Yeah.
So it's PV equals nRT.
Yes.
So I get N's the variable that we're solving. What's R?
Oh, so R is the ideal gas constant.
Oh, right.
So is this. Yeah.
Okay.
That's R. Okay. Okay, cool. Any other questions? We're not going to do number 3. It's similar just for time's sake. Okay. So now moving on. There is a summary of all the gas laws, everything that we learned. So, yeah. Okay. Units for gas laws. Again, just a refresher, same slide as before. Here's another example. Oh, the same one. Same one, but a different pressure with the spring and the chlorine. So you can try that on your own. Okay, so now let's talk about more things. We'll talk about temperature and velocities. Now, don't really worry about these equations. These equations might look intimidating, root mean square, whatever. Well, this one you might have to know for a question. But let's talk about conceptually what's going on here. So now we're going to talk about how gases speed, kinetic energy relate to their mass and their velocity. So a key definition: all gases at the same temperature, obviously the same temperature, have the same average kinetic energy. Write that down or remember it. All gases at the same temperature have the same kinetic energy. The reason why is because if you took physics, kinetic energy is based on mass and velocity. So if that's the case, let's say, where's the stupid marker? So it's based on mass and velocity. So 1/2 mv squared. Don't really worry about the squared part, but 1/2, it's mass and velocity. Now, if you have a heavier gas, like O2, that's 32 grams per mole, it will move slower, and the kinetic energy will be a certain number. If you have a smaller gas, like hydrogen, which molecular mass is 2, it will move faster, and the kinetic energy will still be the same. My cat's being funny, but it will still be the same as another gas. So they will all balance out. Basically, the way it works is lighter particles will move faster, massive particles will move slower. Think about race car versus truck. They can both have the same momentum or the same kinetic energy, but one's moving faster and one's moving slower based on their masses. So that's basically what this is. And you can calculate that. You can calculate their velocities. So their root mean square velocity is this. So URMS. The square root of RT, which we know R is 0.08206. I think this uses different R. And then T and the molar mass. But are we going to do this? Yeah, I guess we are. Hold on. So we'll get there. One thing at a time. Just know that the lighter ones go faster, the heavier ones go slower. Okay. Molecular speed versus molecular mass. So here's just showing you what I just said. So oxygen, also keep in mind, it's a spectrum. So these gas molecules work in a spectrum. You might have in a container, imagine a large population of gas molecules. Let's say for oxygen. Most of them are moving slow, under 500 meters per second, which is slow for a gas. Some of them, like over here, this is a probability distribution curve. So most of them are underneath here. Some of them are over here near 1,000, very small percent, maybe 1% or less. So the idea is they all follow a bell curve, a probability distribution curve. Things like helium and hydrogen, they're lighter, they move faster, they have more degrees of freedom. So on average, the velocity will be faster. But there are some molecules of helium gas that move slower than oxygen gas. Same thing with hydrogen. Look how broad the spectrum is. And as you can see, the spectrum follows the size of the spectrum, relates to the molar mass. As you get lighter, the gas molecules, yeah, on average move faster, but they have more degrees of freedom and more and a wider variety of velocities. So just keep that in mind. Okay. Now there's different ways to represent this, the root mean square velocity. Now in this case, R is going to be the different R, but I'll let you know that. So ideal gas law, you have 0.08206. For the root mean square velocity, the equation down here, this one, you have 3RT, where R is going to be 8.314. T is your temperature in Kelvin again. N is your number of, N is Avogadro's number, and an M is your molar mass. So it differs a little bit. So basically what's going to happen is, as your molar mass increases, the root mean square velocity decreases. Ignore the square root for now, but you can see how that works. At a certain temperature, basically the only things that are not constant here are temperature and molar mass. R is a constant, 8.314, and N is a constant, Avogadro's number. The molar mass will change based on what gas you're talking about. The temperature will change based on what temperature you're talking about. So if you see that the mass increases, that means the root mean square velocity will be less because it's in the denominator. The temperature will increase. That means the root mean square velocity will increase because it's in the numerator. So that equation will be given on the exam, and it should be fairly easy to use. If I give you a gas, I'll give you oxygen gas at a certain temperature. What's the root mean square velocity? And how does that compare to hydrogen at the same temperature? So your job would be to fill in both of those equations for oxygen and hydrogen, and then compare the two results. Any questions on that? No? All right. Oh, yep, there is a question. Nah. All right. Thanks, Gabriel. Okay, good. So now, this is just saying that as the speed increases, as the temperature increases, the speed increases. We know that already, but I don't want to keep saying the same thing over and over again. But like I was saying, with as you decrease the molar mass, the speed increases and the degree of freedom increases, meaning the spectrum of how fast or how spread out the velocities can be also increases. And the same thing is true for talking about the same gas at different temperatures. So here's nitrogen, for example, at 273 Kelvin, which is 0 Celsius. So pretty cool. Oh my God, what is she doing? Stop. Fucking cat. Sorry. It's like destroying my monitors, and like I don't want her to break anything. So at 273, here's the distribution curve. It's very, very small, very narrow. As you increase temperature, you are increasing the average velocity, but you are also spreading out the spectra, meaning there's more degrees of freedom. Some molecules will move slower, some will move faster, but on average, they are faster at a higher temperature. Okay, so let's do this. Let's do a root mean square real quick. So let's calculate the root mean square velocity of oxygen gas at 25 Celsius. So just like what I mentioned before, well, the math is right here. So you're using this equation, square root of 3 RT over MM. So, or you can use Avogadro's. Where's the Avogadro one? Hold on. Oh, doesn't matter. Oh, so, oh, sorry. I'm sorry. This M is not molar mass. This M is the mass of a sample. My bad about that. So molar, Avogadro's number times mass is molar mass. That's what makes sense. Okay. So big M, MM like this, that's molar mass. A little m like this, that is just the mass in grams of a sample. Multiplying that by Avogadro's number, you get molar mass. Let's get back to this. So root mean square velocity, square root of 3 RT, R is 8.314, P is 298, molar mass is 32, and it's grams per mole. They just wrote it in kilograms per mole, but you do need to do that because yeah, it's another thing. So you do need to write it in kilograms per mole, not grams per mole, because the constant 8.314 is in kilograms. But the easy way to do that is to always just check your units. Always check your units because you'll be given R, both R's, and you'll be given the units for both R's. So you should be fine with that. And you can see how they cancel out. So basically the way to convert grams per mole to kilograms per mole is taking the grams per mole times 10 to the negative third. And that's it. So, and then you get 482. Sorry that was a little bit convoluted and I was all over the place, but is there any questions on that? I'm sorry, because it's just there's mayhem going on behind me. I don't want to stop the lecture. But yeah, any questions?
Is kilograms per mole larger than grams per mole?
The same number, so the same value. So kilograms per mole is just saying how many kilograms are in a mole, right? If grams per mole is, let's say for oxygen, 32 grams per mole. How many kilograms per mole is that? It's a smaller number, 0.0032.
Oh, okay. Yeah, I get it.
Okay, cool. It's just converting from one to the other.
Yeah.
Yeah. Okay, cool. All right, so diffusion and effusion. We'll go through this quickly. It's not that big of a deal. There may be one question or maybe none. You know, I'll put no questions on it because it's not. It's good to understand definition, but the laws aren't really. You don't really use them in anything else. So anyway, so diffusion. So diffusion is when, again, you go from. I talk about this gradient thing, right? So diffusion of gases is when molecules go from a high concentration to a low concentration. And for gases, go from a high pressure to a low pressure. And concentration, same thing. Same effect, called diffusion. So just know that definition. Then you have effusion. So effusion is not related to diffusion really at all, even though they sound similar. Diffusion refers to the movement of molecules of gas moving through a small hole into a vacuum. So basically, it is going from high to low. It's going from really high concentration to no concentration. But the rate at which the gases go through depends on their size. And it depends on their root mean square velocity, which is the same thing as their size, which also depends on their size. So here is how effusion works. So effusion, you have a vacuum in here in the right chamber, and then the gases are on the left side. If you make a very small hole, small meaning about the size of the molecule, like a little bit bigger than the molecule, that's how small I'm talking about. Anything bigger, it'll be just like having an empty room. It wouldn't matter, but very, very small hole. nanometers. And you let the gases go into the vacuum. The rate at which they go through depends on their average velocity, depends on their kinetic energy, or really depends on their mass. And there's an equation to govern that. So that equation is based on molar masses. Now this big M is molar masses. And the rate of a fusion of gas A, let's say it's oxygen, the rate of over the rate of a fusion of gas B, let's say it's hydrogen, is directly proportional to the square root of mass B, molar mass B, over molar mass A. So let's do this. Let's do an example with this. I might give this on the test. It's fair game, but there might be one. I'll say that. It's not too hard. So rate A over rate B. So let's say gas A is O2. Gas B is H2. So we know that gas A will move slower. It will effuse slower because it's bigger. Gas B will effuse faster because it's smaller and it has a higher average velocity. So now, if we do the ratio of these, slower versus faster, you'll get a number that's less than 1. That should be this answer, the ratio of the rates. If we put the molar masses into this formula, let's see what we get. Molar mass of B, which is 2, the molar mass of A, which is 32, you get the square root of 1 over 16. Reducing this fraction, you get 1 over 16 equals 1 over 4. So you do get a number that is less than 1. That means the rate of A, the rate of oxygen gas exchange, is 1/4 of the rate of gas B, which is hydrogen gas exchange, meaning the hydrogen moves 4 times as fast through the effusion hole that gas A oxygen does. So that's really all you would need to do with that equation. Is there any questions on that, or do you think that's a fair thing for you guys to do? Any questions? No? Okay. Okay, moving on. All right, so the next thing we're going to talk about is the standard conditions of gases. And there's this thing called STP. So here's STP. So STP stands for standard temperature pressure. T is temperature, P is pressure. And for gases, we can say that a lot of gases exist at STP, which is 0 Celsius, 1 atm, in in lab conditions. So labs, we try to make, if we're doing gas experiments, which I've personally never done, but I know people that do, they have different chambers where they keep their gases at STP in order to make calculations easier, to make a standard condition, a standard environment, so that their results can be compared to other results around the world. So this means the standard pressure is 1 atm and the standard temperature is 0 Celsius. So pretty cold. Now, we can say things about the standard temperature pressure. And also, you need to know this too. You need to know STP means 1 atm, 0 Celsius, or 273 Kelvin. Better to remember that. We can say different things. In the calculation, we can say that the molar volume, meaning the volume of 1 mole of gas at STP, is 22.4 liters. And that's true for all of them, for mostly all of them. This really refers to an ideal gas, but basically 1 mole of gas at STP is 22.4 liters. If you do the V equals nRT equation with STP, you'll get that answer. So you can have this definition in the back of your brain if you ever get into a lab, that you know if you're doing gas experiments, if you're working at STP, 1 mole is 22.4 liters of it. So that's a good thing to know. And here you go, as an example with different gases. You have helium, xenon, and methane. You see that 1 mole of all of them at STP is 22.4 liters, almost exactly. Sometimes it does vary, but very, very slightly. So that's important to know. Okay. So then from knowing the molar volume, you can figure out the density of a gas. So the molar density, or really the density of a gas, is described by its molar volume divided by its molar mass. So think about molar mass and molar volume as units. Molar cancels out, and you get mass over volume, which is your density. So if you have 1 mole of, let's do an example. If you have 1 mole of oxygen, we use oxygen, the molar mass of it is 32, and the molar volume of it is 22.4 at STP. This means that our density is 1 point something. Maybe around 1.45 or something. I don't know. So yeah, so that's how you would figure out density at STP. But you can also figure out density at any condition, because you know how to figure out the liters or the volume of any gas at any condition because you have your formulas. You have your combined gas law and your ideal gas law. So here's examples of that. And it would be in grams per liters, because that's how the units will go. Okay, so you can also deduce this formula, which will also be given on the exam, to determine the density of a gas, which would be P, which is your pressure of the gas. And this is not an STP. This is generally. But you can figure this out using PV equals nRT, like I mentioned, by figuring out the volume and then knowing the molar mass of it. You can just divide those two, but they simplified it in another equation. You got the density equals the pressure times the molar mass over RT, which basically what they did is replace N and V, and they did the manipulation here, and they got it to be the molar mass. So that would be the density. Again, if you can deduce it just from understanding the concepts that we talked about before of getting the volume of the gas, getting the mass of the gas, dividing the two, you'll get the same answer. Okay, so this part, not too bad. We're almost done, almost. A decent amount of stuff left. A lot of it is not going to be tested on, but this is the last part that is really going to be drilled down, and it's partial pressures. So for partial pressures, what that means is if you have a mixture of gases, so let's say in most cases we're going to have a mixture. It's not going to be a pure gas, like the air. So here's the composition of dry air in this table. Nitrogen is 78%, oxygen is 21%, argon is 0.9%, carbon dioxide is 0.04, and there's other ones that are trace amounts. But these are the main ones. What you can say is that if all of them together have an atmospheric pressure of 1 atm, meaning combined, there it is. So if you have a combined of 1 atm is the total pressure, then you can say 0.78 atm is for nitrogen, 0.21 atm is oxygen, 0.009 atm is argon, and 0.0004 atm is CO2. That's what you can say. So basically, with knowing a total pressure and percent by volume, there's a lot going on here. Percent by volume, right? And I can say that the percent by volume is equal to the percent by pressure, or by all the pressures add up. If I had 1 atm total, you can use those percents to figure out the partial pressure. And this phenomenon, the reason why you can do that is because, like I mentioned in the kinetic molecular theory of gases, that all of these gases are so small that their size and their velocity doesn't really determine, or doesn't really change their pressure in an open world. It doesn't really change their pressure in comparison to one another, or their size. So their size is so negligible that you can say that the percentage gases in an environment is the same percentages in pressure than it is in volume. Same percentage by volume is the same percentage by pressure. So is there any questions on that? Because I said that weird the first time. And we're going to use that information in a second in this equation. So this equation is the equation of partial pressures. Very simple. Basically saying that if you have multiple gases and you add up the pressures of the gases, you will get the total pressure of the atmosphere or whatever container you're dealing with. So that's very simple. And also this will be given on the exam too. So for a mixture of gases, the total pressure is equal to the sum of the partial pressures of the individual gases. So not too bad. Now, this is just saying you could use PV equals nRT to solve for the pressure of gas A and B, and then add them up to get the P total. We know that. We can figure that out already. But let's say I give you an example. Let's say I give you a question on the exam where it says you have gas A has a certain PV equals nRT. Gas B has a certain PV equals nRT. You solve for P for each one of them. And then the question is, what is the total pressure? And then you can add them up. And you can basically just add up the PVs and RTs. So you can do that. And also, another thing to keep in mind is, since the gas identity doesn't really matter because they're so negligible in size, the moles, the amount of them, can be used to determine, just like for volume and pressure, the percentages can be used to figure out each one. The mole, the number of moles, can be used the same way, and you can develop a mole fraction. So basically, all you need to know is you can use PV equals nRT to find P, add them up to get the total pressure. And also, I'm sure a lot of you are overwhelmed, some of you maybe, that there's a lot of information here. But on Moodle, there is, I'll show you Moodle in a second. I'll show you, well, you can see on Moodle, you'll see it, that there's a gas law practice worksheet with the answers. So it's not going to be graded or anything. I definitely suggest working on that in your spare time when you're studying, and it'll help you just doing repetitions of these kind of problems. That, along with the homework, will really make you strong for the exam. Okay, the mole fraction. So the mole fraction is basically the fraction of moles over the total moles of a certain gas. So the mole fraction is this definition right here, but knowing the percent pressure, the partial pressure percentage, let's use nitrogen as an example. I can keep talking, but it's better that we use examples. So nitrogen, N2, is 78%. This means the pressure is 0.78 atm out of 1 atm. Meaning total atmosphere is 1, partial pressure of nitrogen is 0.78. You could also say that the molar ratio, the total moles, let's say you had 1 mole total, you would also have 0.78 moles of nitrogen of N2. This is saying that the partial pressure percentage is the same percentage as the mole ratio, the mole fraction. Thus, you could say the mole fraction, this X, which is actually a Greek letter, psi or something, sky, I don't know, one of them. It's been a while since I was in the frat. But so the mole fraction is the number of moles of that specific gas divided by the total moles. And that percentage is equal to the volume percentage and also the pressure percentage. So a lot of these things are equal, so it might get confusing. But yeah. And then another way you can write this is the mole fraction percentage times the total pressure equals the partial pressure for that gas. So let's say the mole fraction of nitrogen is 78.78. The pressure total is 1 atm. That means the partial pressure is 0.8 atm. So we end up with that same answer. It's kind of like going backwards from the initial equation. So mole fraction is equal to pressure fraction. So keep that in mind. And again, this will be given on the exam, that one. Okay, so same thing. Here, look, oh, I did this example already. Nice, cool. So this is really just saying what I said and giving the example. Nice, 78%. We did that already. Okay, here's one. So find the mole fractions of gases in a 12.5 liter tank with 24.2 grams of helium and 24.32 grams of oxygen at 298. So find the mole fractions. First, you can find the moles since you're given grams. So dividing helium. So helium grams is 24.2. Dividing that by the molar mass of helium, which is 4, gives you 6.05. Doing the same thing for oxygen, you have 4.32 grams of oxygen divided by 32 equals 0.135, here's a typo. Here we go. Equals 0.135 moles of oxygen. And the volume and the temperature are there too. But the volume and temperature doesn't really matter for this case because we're being asked for the mole fractions. So we can figure out the mole fractions. Now, if you add up the total moles, you get 65 or 6.185, I think. Is there a question? Okay, Chris, you're good. Yeah, the lecture is going to be on Moodle on YouTube, so you can finish watching it. Cool. Okay, so you add up both of the moles, and you see that you're doing that right here. You get 6.185, and that has to be the total. Then you can figure out the mole percentage or the mole fraction of each gas. Helium, 6.05 divided by the total, you get 97%. Oxygen, the 0.135 divided by the total, you get 2%. So that's how you do that. That's how you can figure out mole fraction. And then you can do the same thing with partial pressures. So find the partial pressures of a 12.5 liter tank with that much stuff in it. So you can do the same thing. You can use the same numbers. Basically, there's different ways to approach it. You can figure out the partial pressure of each gas using PV equals nRT for each gas, because you have that. You have the pressure, you don't have the pressure. So you can find the total pressure. So you can find P1 using the moles of helium, the temperature, and the volume. And you could find the pressure for each one, add up those pressures, you can get total pressure. Or going from the previous example, you can do this equation, this problem using the mole fraction of each gas multiplied by, in this equation right here, the mole fraction of each gas multiplied by the total pressure, which is found by doing only one PV equals nRT for the entire mixture with the total moles. So does anybody want me to do this problem here?
Yeah, I have a question.
Yes.
Can you explain how they got the 0.97817?
This one? So that's from the previous problem. So that is here, where it's the mole fraction of helium. So the moles of helium divided by the total moles of gas in the mixture, and you get at 97%, 0.978. And then you can use that mole fraction, multiply it by the total pressure, because the pressure percentage and the mole percentage is the same. Multiply them together, and you get the partial pressure of helium.
Okay.
Okay. I'm going to do this example. I'm going to do this one. So just so everyone's on the same page. I feel like I'm just like randomly explaining stuff. I don't like that. All right. So, not duplicate. I don't mean to duplicate. New slide. Okay. So we're going to take this, put it there. Okay. So from the previous problem, we know that the total, or the mole fractions for our samples, our helium is 97%, oxygen is 2%. So from that, we can figure out information. So there's two ways to do this, like I said, but we'll do this one of the ways. So find the partial pressures. All right. And where's this is annoying. All right, so partial pressures. So we know that the partial pressure of helium, or any gas, is equal to the mole fraction times P total. The same thing is true for oxygen. Mole fraction of oxygen times P total. So now the only thing we don't have is P total, but we can figure that out. So the total pressure, P total times V total, equals N total over, or times R times T. So we're doing 1 PV equals nRT, and we can solve for P. So PT we don't know. VT we do know. Total volume is 12.5. 12.5 equals N, which is the total moles, which we also know, 6.185 times our ideal gas constant times our temperature, which is 298. And we divide all of this by 12.5, and we get our P total is going to equal this. That's 12.1. All right, so 12.1. Okay, does everybody understand how I got that? I did the total pressure, PV equals nRT. So now that we have PT, the total pressure, and we have the mole fraction of each mole, of each gas, you can figure out the partial pressure of each gas. So it would simply just be, for this one, it would be 0.98 times 12.1. For this one, it would be 0.022 times 12.1, and you get the answers for both. That's one way to solve this. The reason why I feel like I'm just like rattling off variables. The reason why is because there's multiple ways to solve this. The alternative would be to do 2 PV equals nRTs. You do one for helium, one for oxygen. Find the partial pressure of each one, because you do know the moles of each one. Once you find the partial pressures of each one, you're done. That's it. Or you can add them together and get the total pressure, and then do this, which is the same thing. So once you have the partial pressures, you can do it. So, and I'm gonna set those up for helium and oxygen. So helium, it would be, so P helium, we don't know. H helium, it's 12, because the volume is always constant for a container, equals N. So the moles of helium we don't know, but we can figure it out with the grams. 24.2 divided by 4, that's how many moles it is, times R, 0.08206, times T, which is 298. So you're solving that one for helium. And then for oxygen, you would be solving this one. 12.5 divided by 4.32 grams divided by 32, which is the molar mass of oxygen, times 0.08206 times 298, and you would get your answer for PO2. And these answers should be the same as these. All right, so I know that was a lot. Any questions on that? We're almost done. Okay, so whatever, not really too important. This is just, now something we can do is we can also use what we just learned in stoichiometry. So we're basically combining everything that we learned so far. So this question, how many grams of water form when there's 1.2 liters of H2 at STP completely reacts with O2? Okay, so this means that we want to figure out how many moles of gas. From all this information, we can figure out how many moles of gas. And because it completely reacts with O2, we know that H2 is limiting. So H2 is going to go through the reaction completely. So using P equals nRT, we can solve for the amount of H2 at STP. If we can, and actually, watch this. Because we know what STP is, we know that 1 mole at STP equals 22.4 liters. We have 1.24 liters. We can just do 1.24 divided by 22.4 to figure out how many moles. And that's going to be around 1 over 11, whatever. Let's say it's 0.10 moles. Now, using that, we can say, okay, if this reaction balanced says that 2 moles, or how many grams of water form an H2? Okay, so it's asking for how many grams of water. So we have 2 moles create 2 moles of water, all right? So 0.1 moles of H2 make 0.1 moles of water. Multiply that by 18, and you get 1.8. 1.8 grams of H2O, approximately. So does that make sense how you can tie in the molar, gas stuff to stoichiometry and different questions with reactions? If you have any questions, please let me know. No? Okay. So the last thing we're going to cover is that all gases are not ideal. So this ideal gas thing, STP, whatever, it works for low pressures and normal temperatures, meaning atmospheric conditions, maybe 0 Celsius, whatever, but nothing like extreme conditions in a laboratory. That if you want to do extreme conditions, it definitely varies a lot. But basically, I'm going to cut to the chase here. There's these constants that can be added to a to the equation, to PV equals nRT. So I'm going to skip to I'm going to cut to the chase here. So this is called the van der Waals equation, which is basically PV equals nRT modified for real world conditions. And no, you're not going to have to use it, but I'll tell you what it means. Basically, there is 2 corrections. There's a correction for pressure, and there's a correction for volume. Because the pressure and the volume of an ideal gas might be are assumed without using the forces associated, because we assume there's no forces and we assume the volume is negligible. Those are the 2 big assumptions we're making. We're assuming, I'll say it again, we're assuming volume is negligible, meaning the sizes of the gas particles are so small that they don't matter. And we're assuming that there is no intermolecular forces between the gases, meaning they're not reacting together at all. But at extremely high temperatures and extremely high pressures, some of these rules are broken, and there might be some intermolecular forces. The size, since the molecules will be pushed at high pressures so close together, the size may play a role in the volume. So you need to correct for those when we're dealing with extreme cases. Most of the time, doesn't matter. But for extreme cases, it does a bit. So here's what we need to do. This constant A, there's different A values for every type of gas. And that corrects for the intermolecular forces in each gas at really any pressure, but normally at very, very high pressures. B corrects for the size of the gases. And you can see how for bigger gases, B is bigger. That's not necessarily true. Generally, yeah. So like Cl2 is pretty big, 0.05. H2O is smaller, 0.03. Oxygen is smaller, 0.03. Yeah, so it's about relative to size. Xenon's pretty big, it's 0.05. So relative to size. So those are two corrections that can be made on pressure and volume that are used for real gases. And the rest of it's the same NRT. But I just wanted to let you know that exists. And there might be questions on the homework about it. In that case, you can refer to this chart for the A and B values. And then everything else in the equation, N is just moles, N is moles, V is volume, just like it normally is. So that should be there. So any questions on that? So basically, ideal gases, we're assuming a lot of things. The main two things is we're assuming that there are no intermolecular forces between the gases, which at low temperatures and normal pressures, it's true. But when we make everything extremely high, that might get thrown out of whack. Also, we are assuming that the particle size doesn't matter, or it's negligible. Any questions? All right, then we're basically done. So that's the same thing. And here's just an example of, here's to show you something. Ideal gases. See this line right here? If we assumed all gases were ideal at every temperature and every pressure, we would be here. This y-axis, x-axis is pressure in ATM. Think about it, ATM. So even when you get to 50 ATM, which is considered a very high pressure. Think about it. One is our atmosphere. You go on a roller coaster or something, or no. You go to the Gravitron or something in like a carnival. It's like maybe 2, maybe 3. Think about 50. That's crazy. That would rip you in half, 50. Think about 200. So these are extremely high pressures that you can see how the curves for these different gases get thrown off a lot. And then the ideal gas law wouldn't really be much of help to anybody. So you need to use the real gas corrections. Okay, so that's enough of me talking. Here are some more gas problems for you guys if you are bored. And there's some on Moodle as well. So is there any questions before we split into breakout rooms to do the homework? Remember, basic homework for chapter 6 is due tonight. You can do it now. I'll leave the room open until 12, and that's it. So I will end the recording right now. Stop recording.